So my name is Rémi Vaucher. I'm a PhD student at Université Lyon 2. More particularly in ERIC Laboratory, under the direction of Professor Stéphane Chrétien. I passed my PhD jointly with Alias Technology company, and I will present our work on the algorithm of from Siegel, Pfeffer, and Sturmfeld. So, what do we talk about? The algorithm is made for recover the matrix decomposition of paths in a given basis. So a path is just a d-dimensional function of time. And to recover this matrix, we use the third order signature of the path. So it's a beautiful algorithm in the sense where you don't need to have the path, you just need the third order signature. And you can recover your matrix decomposition. In fact, it was applied on theoretical paths, but not on paths with a bit of noise. And it happens that the signature is highly sensitive to noise, so it will we will have problem to estimate the expectation of the loss. In the last part, we will propose a new estimator for the expectation that is more robust to the noise. Okay, let's talk about signature. We will use the extracted signature of order k. So it's just a high dimensional tensor. Which every component is calculated with the iterated integral of the component of the path. So signature is a powerful tool to extract information feature, geometric feature of your path, and you have many useful properties, like invariance with respect to reparametrization. In the sense of if you travel through your path at a different speed, you don't change your signature. Another useful property is the shuffle product that gives a link between order of signature. You can explain shuffle product quite easily with basic tool of geometry. In this example, you can see that product of coefficient of the first order signature is equal to the sum of coefficient of the second order signature. In fact, when you see the right side, you have the area of a rectangle, and on the left side, you have the product of two lengths. So you are coherent, two lengths multiplied gives an area of a rectangle. Okay, last but not least, a chance property that is very important for a statistician. Chance proves that if you take the signature of the concatenation of two paths x and y, you just have to compute the tensor product of the signature of x by the signature of y. It is very important for a statistician because observed signal are every time discrete. You cannot have a continuous recording, and so you have your signal at a certain timestamps. But you can pass to a continuous version of your path by interpolation, by linear interpolation between two consecutive pair of points of your path. With this continuous version of your path, you can compute the signature with chance property. Okay, let's talk about the algorithm of Segal, Pfeffer, and Sturmfels. So assume there exists a basis Psi and a linear map A such that A is the matrix decomposition of X in the basis Psi. Segal, Pfeffer, and Sturmfels prove that the third order here signature of X is just the third order signature of A Psi and is given by this bracket product that is just the sequence of K mod tensor product. So I will call this bracket product multiple K mod product just for simplicity. The tensor Cpsi is the third order signature of the basis Psi. You can see that you have a formula for every coefficient, and you can note that this coefficient is a polynomial with respect with a coefficient of matrix A. That will be important in a few slides. Okay, in practice, signal is just pure signal with noise. So we will note X, the observed signal, X star, the pure signal, and epsilon, the additive noise that you can have with observation. You can see it as a discrete path or continuous path bar linear interpolation. And in our paper, for simplicity, we assume that epsilon is a Gaussian white noise function. The main problem that we study is first estimating the signature tensor of X star, so the pure signal. Then with this signature tensor, recover the original signal with the algorithm of Segal, Sturmfels, and Pfeffer. But as I said, signature is highly sensitive with noise. So it will pose problem. In the first part of the presentation, we study anti-concentration property of the coefficient of the noisy signature tensor, and in the second part, we propose the Momov-Means estimator to estimate the expectation. So one standard approach to estimate the third signature. The third order signature of the expectation of X, that is only X star, because epsilon is as expectation equal to 0, is just to solve the following least square problem. So you minimize the squared error. And if you take an orthogonal basis, you can decompose epsilon in this basis, so you get an IID Gaussian matrix, and you can put this in the signature tensor. So you have that the third order signature of X star plus epsilon is just the third order signature of the matrix A star plus E applied to Psi, and is given by the multiple K product of C by the matrix A star plus E. So to make the problem finite dimensional, we compute the signature of X star plus epsilon with an approximation in a timestamps. And we use some simplification of notation for the multiple K-mod product. So it is easy to see that the multiple K-mod product of C by A plus E can be decomposed in a sum of four terms. The first one is just dependent of A. The second is dependent only on E. And the two last are dependent both of A and E. As we seen before, the coefficient of this tensor is a polynomials, but it is a polynomials in coefficient of E, so in Gaussian random variables. We have this formula. So a coefficient of this tensor can be expressed as the sum of four polynomials, polynomials that can be summarized in one polynomial P. And depending on the coefficients alpha, beta, and gamma, you can have P multilinear or not multilinear, but of degree D, D equal 2 or 3. We have two theorems that permit to give an anti-concentration properties to this polynomial. Is alpha equal beta equal gamma, we have a multilinear polynomial. Under assumption of on the distribution of the EE, of the EI, we have the property of anti-concentration. These assumptions are fulfilled by Gaussian distribution. For the two next case, we use this theorem. Again, we have a strong assumption of the distribution of the random variables. Each random variables must fulfill an anti-concentration, a sort of anti-concentration property. This is fulfilled by the Gaussian distribution, so we have the anti-concentration properties for all coefficients of the tensor. And so we now must dodge this problem. So I will present the median of mean principle in general, and then I will apply it on our problem. So we consider an IID sample of a random real-valued random variable. So we have a sample, and you want to estimate the expectation mu p. You fix k and b such that n equal kb, and you create k subset of the set 1n as a partition, and this subset must be of cardinality b. For each bi, you create the empirical mean of the subsample of x, of the sample of x, defined by bk. So you have multiple empirical mean, one for each bk. The mom estimator is just the median of all these empirical means. We will establish concentration for suprema of mom that give us a theoretical guarantee of reaching the expectation, but we need this coefficient df, that is the Radmacher complexity of a class f of function. We will compute it later. So recall a bit of context. We will just note that on x, we will note that x is a sample on timestamp t nu. We will not say it on cpc. It's the same timestamps. We compute the signature of psi on the same timestamps that x. Okay, so given a positive integer nu, we create a random set of timestamps t nu, and we want to estimate the expectation with respect to t nu and epsilon of the squared error. If you want to get the mom principle to work, we need n sample of this variable, this one in the expectation. So y is just the squared error evaluated on the timestamps t nu. We need a sample of n of this variables. So we create n timestamps with the same distribution as t nu, and so we create each yi that is the squared error of the squared error evaluated in each t nu I. You can notice that the epsilon t nu e are IID, and so is the signals. And based on this assumption, we create our B and K as earlier. We create our empirical means on each BK as earlier, and we got that mum of Y is of Y is the median of this set of means. Okay, to apply theorem 1, we need to compute the Radmacher complexity on F. F being the set of the function that maps epsilon t to the Pythagore development of the squared error. We skip the technical part; it's not relevant for this conference. And we found this afternoon a result that is more sharpened than this one. So irrelevant. And I just want to talk about this article, Chrysos, from Chrysos. He studied polynomial nets. So he creates a neural network to fit a polynomial. And we use these results to calculate Radmacher complexity, because he does that for polynomial nets. Each polynomial can be created as a polynomial net. It's a beautiful paper. Irrelevant. And so we reach our final result. So we have finally concentration of the suprema of mum by computing this quantity. And so we know we have a theoretical guarantee that mum will reach the expectation we want. And this finishes my presentation. Thank you for your attention. If you have questions, I'm glad to answer it.
Questions?
A question that one might have is, you see the signature is something in continuous time. Here you have this discrete time, and then in order to compute the signatures, you have this linear interpolation, right? That's how you do it. So in order to compute the signatures to third order, you go from the discrete data set to a continuous curve by using a linear interpolation, I guess, right?
Between consecutive time steps.
Right.
You get a time series, a sharpened time series.
Right. So the question would be how your results, and in particular the last theorem that you showed to us, how is that dependent from the interpolation that you are using? You see in other empirical papers with signature, they go for this lead-lag transformation, or they use these different techniques. But I never know, one question that always comes to me is...
This is a good question. You can see if you have timestamps that fit exactly the time of observation, you have no problem. And if you go just between two observations, you can see this point as pondered average of the two observations. So logically, that must not present a major problem. But I did not think about that.
Other questions? I have a short one. So in this result that you were showing, you were using the ZIAD assumption. And you're working with time series, so probably I missed that, but you're taking these timestamps and you're taking the time series observations. So where can you use the ZIAD assumption in this setting? So doesn't it violate it?
Is used in fact we prove anti-concentration properties that does not happen every time. We just want to say that sometimes it happens. So maybe you will not have something IID, maybe you will, but in some time when you have IID, some theorems tells you that you have an anti-concentration problems, and so you have I don't know if
Okay.
that answers
Yeah.
to your question.
Yeah. More questions? Okay, we should thank again Remy and the winner.